there is a number that, by every rule you were ever taught, cannot exist. Multiply it by itself and you get a negative, which nothing is supposed to do. For centuries, the greatest mathematicians alive called it impossible, absurd, a fiction. And yet, that impossible number now runs the electricity in your walls, the signal in your phone, and the deepest equations of physics. This is the story of how humanity was forced to invent the unthinkable. To understand where it came from, you have to understand a stranger world, Renaissance Italy in the early 1500s, where mathematics was not a quiet academic pursuit, but a blood sport. Careers, reputations, and livelihoods were won and lost in public, and the weapon was not a sword, it was an equation. Here's how it worked. A university post wasn't safe for life. A rival could challenge you to a public contest, a cartello di sfida, a written cartel of defiance. Each mathematician handed the other a list of problems. Whoever solved more, in front of witnesses, won. The loser could be humiliated out of his job. Math was a duel, and the whole city came to watch. Which meant that a new method, a way to solve a problem no one else could, was not knowledge to be shared. It was a secret weapon. If you could solve equations your rivals couldn't, you kept that trick hidden, hoarded it, saved it to ambush the next challenger. In this world, mathematical discovery was treasure, buried and guarded. And there was one great prize everyone wanted, a problem that had stood unsolved for thousands of years, the cubic equation. Whoever cracked it would hold the ultimate weapon, unbeatable in any duel. It was the Renaissance equivalent of a secret superpower, and the race to solve it would tear friendships apart and, in the end, crack open the number system itself. So what is a cubic? You've met its little sibling. A quadratic equation involves a number squared x times x. People had known how to solve those since ancient Babylon 4,000 years ago. But a cubic goes one dimension further. It involves x cubed, x times x times x. And that one extra step turned out to be a wall that stopped the greatest minds for 2,000 years. The specific form at the heart of the story is called the depressed cubic, a cube plus some multiple of x equals a number. It looks innocent, but no one, from the Greeks to the Persians to the medieval scholars, had found a general formula to crack it. The great Luca Pacioli, Leonardo da Vinci's own mathematics teacher, had flatly declared its solution impossible. Then, around 1515, at the University of Bologna, a quiet professor named Scipione del Ferro did the impossible. Working alone, he found a method, an actual formula, that could solve the depressed cubic. He had cracked the 2,000-year-old problem. He was, as far as we know, the first human being ever to do it. And what did Del Ferro do with this earth-shattering discovery? He told almost no one. He didn't publish it, he didn't announce it. In the dual culture of the time, a solution this powerful was worth far more kept secret, a weapon in reserve for any challenger foolish enough to face him. So the greatest mathematical breakthrough in centuries stayed hidden, locked in one man's private notebook. For years he guarded it, the secret edge, telling no one how it was done. Whether he ever used it to crush a rival, we don't know. But the secret couldn't stay buried forever. Del Ferro was getting old, and a secret that dies with you helps no one. Not even your own students, your own family. So near the end of his life, around 1526, Del Ferro passed the method on. He revealed it to a small circle he trusted, a student of his named Antonio Fiore, and his son-in-law Annibale della Nave, who inherited the precious notebook. The secret of the cubic now lived in a few hands, and one of those hands belonged to a man who would use it recklessly. That man was Antonio Fiore. By all accounts, Fiore was a mediocre mathematician, not brilliant, not original. But now he possessed something priceless, the one method on Earth that could solve depressed cubics. It was as if a middling swordsman had been handed a magic blade, and Fiore intended to use it to make his name. For years, Fiore sat on his inherited secret, waiting. Then, around 1535, he decided the time had come to profit from it. He went looking for a fight, a public contest that would launch his reputation, and he picked his target carefully, a rising, self-taught mathematician making a name for himself over in Venice, a man everyone said was brilliant, but who had come up from nothing. Fiore's plan was simple and, he thought, foolproof. He would challenge this Venetian to a duel and stuff his list of problems full of depressed cubics, the one thing only he could solve. His rival would be helpless, unable to answer a single one. Fiore would win in a landslide and become famous overnight. It was the perfect ambush. There was just one thing Fiore didn't know. The man he'd chosen to humiliate was not some comfortable scholar. He was a survivor, a man who had clawed his way up from poverty and horror, who had taught himself everything, and who did not lose. His name was Nicolo Fontana, but everyone called him Tartaglia, the stammerer. To understand why Fiore's ambush was about to backfire catastrophically, you have to understand who Tartaglia was, and what he had already survived. Because the story of the impossible number runs straight through one of the most extraordinary and traumatic lives in the history of mathematics. The stakes of the coming duel were enormous, not just a job or a title, but possession of the greatest secret in mathematics about to be pried loose at last. Fiore held it by inheritance. Tartaglia would have to seize it the hard way by reinventing it himself alone under impossible pressure in a single desperate night. And beyond the human drama of the contest lay something none of these men could yet see. Buried inside the very formula they were fighting over was a trapdoor, a place where the math would demand a number that could not possibly exist. The duel would hand humanity the cubic. But the cubic would hand humanity a monster. But first, the duel of 1535, and the scarred, stammering genius who is about to shock all of Italy. It begins, as so much of his life did, in violence. In 1512, the town of Brescia in northern Italy was caught in the wars ravaging the peninsula. A French army stormed the town, and what followed was a massacre, days of slaughter in which tens of thousands of residents were killed. Among the terrified civilians was a boy of about 12, hiding with his mother and sister. His name was Niccolò Fontana. The family took refuge in the cathedral, praying the sanctuary would protect them. It did not. A French soldier found the boy and struck him across the face with a saber, vicious blows that split his jaw and sliced through his palate. He was left for dead on the cathedral floor, his face a ruin. By some miracle and his mother's desperate care, he survived. But the wounds left him with a lifelong speech impediment, a stammer, from the damage to his mouth. Cruel classmates gave him a nickname for it, Tartaglia, the stammerer. It was meant as a taunt. And in one of the small acts of defiance that defined his life, he took the insult and made it his name. He would be Tartaglia, and he would make the name famous. His childhood was crushing poverty. His father, a humble mail rider, had died when Nicole was 6, plunging the family into destitution. There was no money for school, barely money for food. The story goes that he was so poor he couldn't afford paper, and practiced his mathematics on gravestones in the cemetery, using the tombstones as slates. And yet, almost entirely self-taught, he became one of the finest mathematicians in Italy. He earned a living teaching mathematics in Verona and then Venice, tutoring, selling his skills. He was proud, prickly, and ferociously intelligent, a man who had survived a saber and starvation and had no intention of being humiliated by anyone. This was the man Fiore had decided to ambush. In 1535, the challenge was formalized. Each man deposited 30 problems with a notary. Each would have weeks to solve the other's list. Whoever solved more would win. The loser to pay for a lavish banquet and, far worse, to suffer public disgrace. Tartaglia opened Fiore's list and felt a chill. Every single problem was a depressed cubic. Fiore had a method, and Tartaglia did not. He understood at once what it meant. Fiore must possess a secret formula for the cubic, the very problem the great Pacioli had called impossible. If Tartaglia couldn't find that formula himself, and fast, he would answer none of the 30. He would be destroyed, publicly, by a man he considered his inferior. Everything he had clawed his way toward would collapse. Now, Tartaglia had actually been circling the cubic for a while. He'd already found how to solve certain types, but not the type Fiore had loaded his list with. So, with the contest bearing down on him, he threw himself at the problem. He stopped sleeping. He filled page after page. He hunted for the pattern that had eluded humanity for 2,000 years, and he had days to find it. For days, nothing. The deadline crept closer. And then, in the early hours of the 13th of February, 1535, it came. In a flash of insight, the whole structure fell into place. Tartaglia saw how to solve the depressed cubic. Alone, under crushing pressure, he had re-derived from scratch the secret that had taken Del Ferro a lifetime to find. And he didn't stop there. Within a day, he had cracked a second form of the cubic too, extending his method further than Fiore's single inherited trick. He now didn't just match his rival, he outgunned him. The self-taught survivor had, in one sleepless burst, become the most powerful equation solver in Italy. The ambush had just turned into a slaughter. The other way around. When the contest was judged, the result was total. Tartaglia solved all 30 of Fiore's cubic problems, reportedly in about 2 hours. Fiore, faced with Tartaglia's varied and cleverer list, could barely solve a thing. It was a humiliation as complete as Fiore had dreamed of inflicting. The mediocre man's magic blade had shattered in his hand. Tartaglia, magnanimous in triumph, even declined the banquet the loser owed him. The victory itself was enough. Overnight, he was famous. He was now the man who could solve the cubic, holder of the most coveted secret in mathematics. And like Del Ferro before him, he had every intention of keeping it locked away. Because remember, in this world, a secret method was a weapon and a livelihood. Tartaglia planned to publish it himself one day, in his own grand book, on his own terms. Until then, it was his. He had bled for it. He had earned it in a single impossible night. No one was going to take it from him. And there, the secret might have stayed, hoarded and unpublished, perhaps for decades, if not for one more player entering the story. A man of dazzling brilliance and boundless ambition, one of the most fascinating and chaotic figures of the entire Renaissance. A physician, a gambler, an astrologer, a mathematician, a man who wanted that formula more than anything. His name was Girolamo Cardano, and his obsession with prying Tartaglia's secret loose would produce one of the greatest mathematics books ever written, and one of the bitterest betrayals in the history of science. The secret of the cubic was about to escape into the world. And with it, the trapdoor no one had yet opened. Girolamo Cardano was one of history's most extraordinary characters, a brilliant physician, perhaps the most famous doctor in Europe, a compulsive gambler who literally wrote the first book on the mathematics of probability, working out the odds at the dice table, an astrologer, an inventor, a prolific author. His life was a whirlwind of genius, scandal, and tragedy. And in the 1530s, he was writing a monumental book on mathematics. Cardano's gambling was not just vice, it was research. Watching dice fall, he glimpsed the hidden laws of chance and became one of the first people to reason mathematically about probability. It's a mark of the man he found deep mathematics in the gutter of the gaming house. But now, for his great book, he wanted the crown jewel, the solution to the cubic. And he knew exactly who had it. Word of Tartaglia's stunning victory over Fiore had spread. Cardano realized that this scarred Venetian held the key to the greatest unsolved problem in algebra, a jewel that would make his book immortal. So he began, politely at first, to ask. He wrote to Tartaglia, praising him, requesting the method for his forthcoming work. Tartaglia's answer was a flat, repeated no. Tartaglia refused again and again. The formula was his life's treasure. He would publish it himself, someday, in his own book. Why would he hand it to a rival to print first? But Cardano was relentless, charming, persistent, and clever. He kept writing, he dangled temptations, and eventually he found the lever that would move the proud Venetian. Cardano dangled a patron. He had connections to the powerful, including the Marchese del Basto, the Spanish governor of Milan, a man who could transform Tartaglia's fortunes. Come to Milan, Cardano suggested, and you might meet him. This could be your path to real security. For a man who had known real poverty, it was bait. He couldn't quite refuse. In March 5039, Tartaglia came to Milan. The patron, it turned out, was away, but Cardano was there and he pressed his case in person. And at last, in that house in Milan, Tartaglia relented, but only on a condition. Cardano had to swear a solemn promise, never to publish the method, never to reveal it to anyone, to keep it secret forever. Only then would Tartaglia share it. And even then, Tartaglia didn't simply write it out. Fearing theft, he encoded the method as a poem, a set of verses that concealed the steps of the formula in rhyme. When the cube and the things together, E, are equal to some number apart, the poem began. You had to already understand the method to decode it. He handed Cardano the riddle, extracted the vow, and left Milan. Cardano decoded the poem and grasped the method. And now he possessed the great secret, but bound by his own sworn word never to publish it. For a man writing the mathematics book of the age, it was agony. He held the crown jewel and had promised not to display it. For years, this stalemate held. Cardano kept the secret, and stewed. But Cardano didn't just sit on the formula. He worked with it. And here, he had a secret weapon of his own, a servant boy he'd taken in named Lodovico Ferrari, who turned out to be a mathematical prodigy. Together, master and brilliant student pushed the cubic further, and then Ferrari achieved something astonishing. He solved the quartic, the equation with x to the fourth power. An even harder problem, cracked. But Ferrari's quartic solution relied on the cubic method underneath it. So now Cardano and Ferrari had a mountain of brilliant new results, all of it chained to Tartaglia's secret, all of it unpublishable because of the oath. The frustration was unbearable. They had extended human knowledge dramatically, and the vow gagged them. Then Cardano found a way out, or convinced himself he had. In 1543, Cardano and Ferrari traveled to Bologna. There they met Annibale della Nave, Del Ferro's son-in-law, keeper of the old professor's notebook. And Nave showed them the notebook. Inside, in Del Ferro's own hand, was the solution to the depressed cubic written decades before Tartaglia's sleepless night. The secret had a father older than Tartaglia. This was Cardano's loophole, and he seized it. His oath, he reasoned, had been not to publish Tartaglia's method. But here was the same method, discovered independently and earlier by Del Ferro. If he credited Del Ferro's prior work, wasn't he free? He could publish the formula as Del Ferro's discovery, honestly noting Tartaglia had found it too, without technically breaking his vow to Tartaglia. It was a lawyer's escape, and Cardano took it. In 1545, Cardano published his masterpiece, the Ars Magna, the Great Art. It laid out the full solution of the cubic and Ferrari's quartic, transforming algebra forever. And Cardano did credit his sources. He wrote that Del Ferro had discovered the method first, and that Tartaglia had rediscovered it and shared it with him. But to Tartaglia, none of that mattered. The secret was out. His life's treasure was in a printed book with someone else's name on the spine. Tartaglia was incandescent with rage. To him, it was theft, pure and simple, a betrayal of a sacred oath. He had guarded that secret for a decade, he had bled for it in a single desperate night, and Cardano had broken his word and printed it. He unleashed a torrent of public attacks on Cardano, accusing him of the vilest dishonesty. The feud exploded into the open. But Cardano, the most famous physician in Europe, would not stoop to trade insults himself. Instead, his loyal former servant stepped forward, Lodovico Ferrari, now a formidable mathematician and fiercely devoted to the master who had raised him. Ferrari challenged Tartaglia directly, and so began a public war of the cartelli, printed challenge letters hurled back and forth across Italy for months. Between 1547 and 1548, the two men exchanged round after round of these cartelli, dense with mathematical problems, personal insults, and wounded pride. It was mathematics as gladiatorial combat, conducted in print for a fascinated public. Finally, it came to a head, a face-to-face contest, the two rivals solving each other's problems before a crowd. The date was set for the 10th of August, 1548, in Milan. On that day, in the garden of a Milanese church, a huge crowd gathered, the contest all of Italy wanted to see. The governor of Milan himself presided as arbiter. Tartaglia, the scarred veteran of the 1535 duel, faced Ferrari, the young prodigy who understood the cubic and quartic more deeply than anyone alive except perhaps Cardano. And this time, the survivor was outmatched. By the end of the first day, it was clear things were going badly for Tartaglia. Ferrari answered his problems and landed the sharper blows. The crowd could feel the tide. That night, rather than face a second day of defeat, Tartaglia quietly left Milan. The contest went to Ferrari by default. The scarred genius who had once shocked all of Italy departed in bitter, humiliating silence. It's a story with no clean heroes. Del Ferro hoarded, Tartaglia hoarded, then was betrayed. Cardano broke a promise, even if he found a loophole to soothe his conscience. Ferrari won, then died young and mysteriously, possibly poisoned by his own sister. Human beings, brilliant and flawed, fighting over a formula, but that formula had a secret of its own, and it was about to reveal itself. So the world now had the cubic formula, printed in the Ars Magna for anyone to use. Turn the crank of the formula, and out comes the answer. Except, sometimes it didn't. Sometimes, right in the middle of the calculation, the formula demanded that you do something that everyone knew was flatly impossible. It asked you to take the square root of a negative number. To feel why that's so disturbing, picture a cubic as a curve. Its solutions, its roots, are the places where the curve crosses the horizontal x-axis. A cubic can cross that axis just once, giving one real root. Or it can wind up and down and cross 3 times, giving 3 real roots. 3 perfectly ordinary, real answers. Now here's the maddening part. You'd think the hard cases, where the formula gets stuck on impossible numbers, would be the ones with no nice answer. The opposite is true. It's precisely some of the cases with 3 clean real roots where Cardano's formula, halfway through, insists on the square root of a negative number. The answer is real. The road to it runs through the impossible. Mathematicians called this maddening situation the casus irreducibilis, the irreducible case. The formula worked in the sense that if you bulldozed ahead to the forbidden step, you'd somehow arrive at the correct real answer. But no one could justify the forbidden step. What could it possibly mean to take the square root of a negative? Square. Any real number, positive or negative, and you get a positive. Nothing squared gives a negative. It just can't be done. Cardano himself ran headlong into these impossible numbers and they tormented him. In the Ars Magna, he wrestled with the related puzzle: divide the number 10 into 2 parts whose product is 40. Work it through, and the 2 parts come out as 5 plus the square root of minus 15, and 5 minus the square root of minus 15. And yet, if you multiplied them together, ignoring the absurdity, you got exactly 40. Cardano didn't know what to make of it. He called the mental effort involved a kind of torture, and famously dismissed the whole business as subtle as it is useless. He had the impossible numbers in his hands, saw they somehow gave right answers, and backed away, unable to believe in them, unwilling to throw them out. The greatest algebra book of the century had hit a wall it could not climb. And there it sat, this scandal at the heart of algebra, a formula that produced correct real answers by passing through numbers that could not exist. For a generation, the finest mathematicians in Europe either ignored the problem or threw up their hands. It took a different kind of mind. Patient, stubborn, willing to follow a mad idea to the end, to break through. That mind belonged to an engineer from Bologna. His name was Rafael Bombelli. He wasn't a famous professor, he was a working engineer who drained marshes and built for a living. But in the 1560s, between projects, he set out to write a clear, complete textbook of algebra, one that would organize everything known and, crucially, confront the impossible numbers head-on instead of flinching from them like everyone else. Bombelli focused on a specific, brutal example, a cubic that lays the paradox bare. The equation x cubed equals 15x plus 4. Written simply, x of in 15x plus 4. Now, you can check by hand that this equation has a beautifully simple answer. Just try x equals 4. 4 cubed is 64. 15 times 4. 15 times 4 plus 4 is 64. It works perfectly. The honest answer is 4. But now feed that same equation into Cardano's formula, the formula that's supposed to hand you the answer. And watch what it produces. It tells you that x equals the cube root of 2 plus the square root of minus 121, added to the cube root of 2 minus the square root of minus 121. It's demanding the square root of negative 21. The formula has walked straight into the impossible, to solve an equation whose answer is just 4. Here, almost everyone stopped. Bombelli did not. He had what he called a wild thought, un pensiero selvaggio. What if, he wondered, you simply accepted these impossible numbers as legitimate objects, at least temporarily? What if you carried the square root of minus 1 along through the calculation, treating it as a real thing that obeys the ordinary rules of arithmetic, and just see what happens? So Bombelli laid down the rules. Let there be a number, call it the square root of minus 1, whose defining property is that, when you multiply it by itself, you get negative 1. From that one rule, he could do arithmetic. The square root of minus 121, he saw, was just 11 times the square root of minus 1. The impossible quantity split neatly into an ordinary 11 and a single strange unit. Then came the leap that must have felt like magic. Bombelli guessed that the cube root of 2 plus 11 roots of minus 1 was itself a tidy little number, 2 plus the square root of minus 1. And the other cube root was 2 minus the square root of minus 1. He checked it by cubing them, following his own arithmetic rules, and it held. The monstrous cube roots were secretly simple. And now the miracle. Add those two cube roots together, 2 plus the root of minus 1, plus 2 minus the root of minus 1. The impossible parts, the plus and the minus root of minus 1, cancel each other out exactly. What's left is 2 plus 2, 4. The formula, forced through the square root of a negative number, cancels to 4. The exact real answer we already knew. The impossible numbers appeared, did their work, and vanished. Sit with how astonishing that is. These numbers that cannot exist were not nonsense. They were tools, real, reliable, powerful tools. You could pick them up in the middle of a calculation, use them to get from a hard question to a true answer, and set them back down. They behaved. They obeyed rules. They gave correct results. Something that impossible has no business being that useful. Bombelli had done something profound. He'd shown that if you treat the square root of minus 1 as a genuine number and give it consistent rules of arithmetic, the impossible step in Cardano's formula makes perfect sense, and the paradox dissolves. In his 1572 algebra, he wrote down those rules carefully. It was the birth certificate of a whole new kind of number. Centuries later, we draw these numbers a home, a two-dimensional map called the complex plane. The ordinary real numbers run left to right along one axis. The new imaginary numbers run up and down along the other. Every one of these numbers, written as a real part plus an imaginary part, is simply a point on that plane. Numbers had escaped the number line and gained a whole extra dimension. And on that plane, the strange facts of the cubic story turned beautiful. Those two cube roots Bombelli found. 2 plus I and 2 minus I sit as mirror images across the real axis, and adding them slides straight onto the real number 4. Better still, the 3 cube roots of any number space themselves out perfectly, sitting at the corners of an equilateral triangle. The chaos of the impossible was hiding a serene geometry. But that acceptance took a long, long time. For centuries after Bombelli, most mathematicians used these numbers only when forced to, holding their noses. The numbers worked, but they felt like cheating. Ghosts that showed up in the algebra with no right to be there. They needed a name, and the name they got was not a compliment. In 1637, the great philosopher and mathematician René Descartes was writing about these quantities, and he reached for a dismissive word. He called them imaginary, as opposed to the real numbers. He didn't mean it kindly. To Descartes, imaginary meant fake, fictitious, not to be taken seriously. a label for numbers that showed up in equations but couldn't correspond to anything actual. It was, in effect, a sneer. And that sneer became permanent. To this day we call them imaginary numbers, and the ordinary ones real numbers. Descartes' loaded 17th century framing fossilized into the vocabulary every student now learns. It's one of the great misnomers in all of science, because these numbers are no more imaginary and no less real than the negative numbers or the zero that people once distrusted just as deeply. Think about it. Negative numbers were once absurd too. How can you have less than nothing? Zero was once a radical, suspicious idea. Every expansion of what counts as a number was resisted, then absorbed, then made ordinary. The imaginary numbers were just the next frontier. They were distrusted for 2 centuries, and then the giants of mathematics made them not just respectable but indispensable. It would take Leonhard Euler and then Carl Friedrich Gauss to finish what Bombelli started, to give these numbers a symbol, a home, and finally full citizenship in mathematics. And once they were let fully in, they did something no one in that Renaissance duel could ever have imagined. They turned out to be the secret language of the physical universe. In the 1700s, Leonhard Euler, the most prolific mathematician who ever lived, embraced the imaginary numbers without fear. He gave the square root of -1 its now famous symbol, the letter I, for imaginary. And with I in hand, he uncovered relationships of breathtaking beauty, binding these once-scorned numbers to the very core of mathematics. Euler found what many consider the most beautiful equation in all of mathematics, e to the power of I times pi plus 1 equals 0. It ties together 5 of the most fundamental numbers in existence, including that, impossible. I, in a single, impossibly elegant line. Far from being a fiction, I sat at the heart of the deepest patterns anyone had ever found. Still, the numbers lacked a picture, a way to see them. That came around the turn of the 19th century. A Norwegian surveyor named Caspar Wessel, and later a Parisian bookkeeper named Jean-Robert Argand, independently hit on the same idea: draw them. Put the real numbers on one axis and the imaginary on another, and every complex number becomes a point you can actually locate. The ghosts finally had a place to stand. Then Carl Friedrich Gauss, the towering prince of mathematicians, put the final seal on it. Around 1831, he championed this geometric picture, made it rigorous and respectable, and gave the numbers a dignified new name: complex numbers. Not imaginary, not fake, complex, meaning simply that each is built from 2 parts. Under Gauss's authority, the 2-century-old suspicion finally broke. Look back over the whole timeline of the feud and its aftermath, and the arc is astonishing. A secret solved in Bologna around 1515, a duel in 1535, a broken oath in 1545, a public war in 1548, a wild thought in 1572, a sneer in 1637, and full acceptance by 1831. 3 centuries to travel from numbers that cannot exist to a cornerstone of mathematics. And Gauss handed the complex numbers their greatest triumph. He proved what's now called the fundamental theorem of algebra, that once you allow complex numbers, every polynomial equation has exactly as many solutions as its degree, every one of them, always, with nothing missing. The imaginary numbers didn't just patch a hole in the cubic formula, they completed algebra itself. They were the missing piece all along. You could stop there, and it would be a satisfying story, a mathematical curiosity, born in a duel, finally understood. But the real shock was still coming. Because these numbers, invented to handle a quirk of the cubic, dismissed for centuries as useless fictions, turned out to be woven into the deep machinery of physical reality. The impossible numbers run the modern world. Start with electricity. Alternating current, the electricity in every wall socket oscillates, rising and falling and reversing many times a second. Analyzing circuits full of these oscillations with pure real number calculus is a nightmare. But in 1893, an engineer named Charles Steinmetz showed that if you use complex numbers, the whole mess collapses into simple algebra. Suddenly, AC circuits became easy to design. That single insight underlies the entire electrical age. Every power grid, every transformer, every motor, every phone charger is designed using the mathematics of complex numbers. The imaginary unit, I, Descartes' fictitious quantity, Cardano's useless torment, is the everyday working tool of every electrical engineer on Earth. It's humming in the wires around you right now. Then there's the world of signals. Every time you stream music, make a call, or load an image, machines are breaking those signals into their component waves and rebuilding them, using a mathematical tool called the Fourier transform, which lives natively in the complex plane. Audio, video, Wi-Fi, radio, medical scanners, all of it processed in the language of complex numbers. The digital world speaks imaginary. And then the deepest layer of all, quantum mechanics, the physics of atoms and particles, the rules that govern the fundamental fabric of the universe. The central equation of quantum theory, the Schrödinger equation, has the imaginary unit I built right into its heart. It is not optional. You cannot even write down the basic laws of quantum reality without the square root of -1. Let that land. The most accurate physical theory ever devised, the theory that gives us transistors and lasers and the microchip in every device you own, is written in a language that requires imaginary numbers. Reality, at its most fundamental level, appears to run on the very numbers that Renaissance mathematicians insisted could not exist. The universe, it seems, does not share their prejudice. Think about the journey that took. A number appears, unwanted, in the middle of a formula, fought over by feuding Italians in the 1500s. It's declared impossible, useless, imaginary. And 4 centuries later it turns out to be nothing less than part of the operating system of the cosmos, indispensable to electricity, to communication, to the fundamental laws of physics. It was never a fiction. It was a discovery waiting to be believed. And that's the real lesson buried in this strange human story. When Bombelli hit that impossible square root, he had a choice: throw it away as nonsense like everyone else, or follow it patiently to see where it led. He chose to follow. And on the far side of the impossible, he found not nonsense, but a hidden layer of reality no one had known was there. It's a pattern that repeats all through science. The thing that looks impossible, useless, or absurd is sometimes just the thing we don't understand yet. Negative numbers, 0, imaginary numbers. Each was once dismissed as a fiction, and each turned out to be essential. Progress often means being willing to work with an idea before you can fully believe in it. And let's not forget the messy, flawed humans who dragged this discovery into the world. Del Ferro hoarding his secret to the end. Tartaglia, scarred and proud, seizing the formula in one sleepless night. Cardano, brilliant and slippery, breaking a promise to make his great book. Fiore, the servant prodigy who won the final duel. Bombelli, the engineer patient enough to think the wild thought. None of them saints, all of them essential. There's something deeply human in it. Great discoveries don't come from serene geniuses in perfect harmony. They come from real people, ambitious, wounded, jealous, brilliant, feuding and striving and occasionally betraying each other, and somehow, through all the mess, pushing human understanding forward. The imaginary numbers were born, not in calm contemplation, but in the heat of a very personal war. So the next time you hear the phrase imaginary numbers and picture something fake or frivolous, remember where the name came from. A philosopher's 400-year-old sneer, not a description of the truth. These numbers are as real as any. They are woven into electricity, into every signal you send, into the deepest laws of the universe we know. Every time you charge your phone, stream a song, or simply flip a light switch, you are relying on numbers that the greatest mathematicians of the Renaissance swore could not exist. Set loose on the world by a poem, a broken oath, and one engineer's wild thought. An impossible idea, patiently followed, became the invisible foundation of modern life. From numbers that can't exist to numbers we can't live without. That's the whole arc. And it turned on people refusing to look away from something that didn't make sense. Del Ferro's secret, Tartaglia's desperation, Cardano's ambition, and above all, Bombelli's willingness to entertain the absurd until it confessed its truth. And maybe that's the deepest thing the imaginary numbers can teach us, that the boundary between impossible and essential is not fixed, that the strange result you're tempted to discard might be a door, and that reality is often richer and stranger and more mathematical than our intuitions want to allow. The universe kept a secret in the square root of a negative number. We just had to be brave enough to believe it. If this story stuck with you, do 2 quick things. Hit subscribe. Neat Science brings another forgotten story back to life, and there's a whole playlist of them waiting for you right now. And tell me in the comments, which part of this surprised you the most? I read every single one. So keep exploring. Your next story is just 1 click away. I'll see you there.